Welcome everyone. So in the morning, we had promised a event packed day, and I hope we are delivering on that. So a very nice panel discussion, discussing various challenges and opportunities on the language AI ecosystem in India. But now let's get into something more technical. Where did it all start? I think you hear a lot of stuff about machine translation nowadays. Where is something new? Was it always around? And that is what I have tried to capture on this slide, right? And some of this does get a bit technical as the intention is of the workshop. So this whole idea of machine translation, right? One of the earliest efforts was way back in 1956. It's known as the Georgetown IBM experiment. You can see that gentleman sitting there with a mammoth machine in front of him, right? And he's trying to do some translation. That's a translation code that is running. And of course, at that time, the interest was English to Russian, and I'm sure you know why. Then that continued for a while, and this is what was like a rule-based system. So you had grammar rules to understand what the sentence is trying to say, and then translate that into another language, Russian in this case. Then, as was the case with AI, as this move happened from rule-based AI to what is known as statistical AI or machine learning-driven AI, the same happened for NLP in general and machine translation in particular. And in 1991, came out what is known as this mathematics of statistical machine translation, a very seminal paper, a very influential paper, which was responsible for driving the machine translation research for the next 3 decades. Till 2011, all the models on machine translation were based on this work done at IBM, which was titled The Mathematics of Statistical Machine Translation, right? And then it continued, right? Like 3 decades, all of it was mainly driven on this particular idea, and hence I have this gap in my history chart, because all of it was that. Then around 2014, that's when deep learning became popular, right? And that's around 2010, 2011 is when it started showing promise in some of these applications in image, and then it came into NLP. And around 2014 came out what is known as the sequence-to-sequence learning with neural networks. This was a paper by folks at Google. And they showed that you can use neural networks for machine translation. Of course, at that time, they were not able to beat the previous statistical machine translation, right, the 1991 models. But what is interesting is within 2 years of deep learning entering machine translation, all the models were able to beat this 30-year of work, which was driving machine translation, right? All these statistical models which had kind of captured the entire machine translation scene, within 2 years, the deep learning-based models were able to excel. And then since then, no one has looked back, right? We don't even talk about statistical machine translation models anymore, right? I mean, in some contexts, yes, but in most cases, what you see is deep neural networks, right? And that journey continued. So in 2015, there was this interesting paper from Mila, which is Yoshua Bengio's group, and I'm sure all of you know who Yoshua Bengio is. And this paper, the attention, what's the main idea here was something known as attention, and that has indeed captured the attention of everyone, right? Whether it be it industry, academia, or startups and so on. And most models have this attention mechanism as a key component today, right? And going from there, right, and you can see from 2017 up to 2022, what has happened is first, deep learning has kind of eradicated or eliminated all the other competition that was there, and it has kept growing on in scale. And I want to focus on the last 3 bullets that you see here, right, or the last 3 points on the chart. The first is the 2020 model by Google, which covered 100 languages. Then the 2021 model by AI for Bharat, which focused on 11 Indian languages and 120 plus directions. And then the very recent work from Facebook, which is aptly titled as No Language Left Behind, where they have scaled up to 200 languages, right? So what has happened in the last 3 to 4 years is the scale of the models has increased along 3 different dimensions. One is the amount of data that these models are trained on. Second is the number of languages that these models support. And third, the number of parameters that these models have, right? So this is like a combination of innovations both on the engineering side, because now you need a large number of GPUs, not just that, very efficient code which can then train these very large scale models, right? And these 3 if I just zoom into them, right? So now I've just cut short my timeline. In 1956, the machine translation model that we had, it was 6 grammar rules, 250 word vocabulary, 60 sentences translated from English into Russian, running on an IBM 701 mainframe. Right? That's what we had in 1956. And let's see where we are in the last 3 years. Right? In 2020, moving from one language, Russian, to 100 languages. Moving from translating some 60 odd sentences, we are training with 13 billion training examples. Right? And with a model which has had 6 grammar rules, we are now at models which have 1 trillion parameters. Of course, they no longer run on mainframes, but you need like 2048 TPUs just to train these models. Right? So that's where the scale has come. And this scale, outside of the big tech companies, right, one of the efforts that we had at AI for Bharat was to train similar scale models for Indian languages. We were not looking at 100, 200 languages, but only Indian languages, and that to 11 of those, covering 121 directions. And we adopted this philosophy of scale, right? So we are training those models on 300 million training examples. These are 1 billion parameter models running on cutting edge GPU infrastructure. Right? And this is the work that I'm going to talk about today. And similarly, we had models from Facebook. I don't know why I left it as XX training examples and YY parameters. But these covered like 200 languages. You can imagine that we have been preparing all of this at the last minute as usual. So 200 languages, XX training examples, which means like a billion plus training examples. Again, billion scale models in terms of parameters and run on a large number of GPUs. You should really read that paper. At the end of that, they have a table which says that the number of GPU hours that they used for training these models. And the scale is just magnificent to say the least, right? So today I'm going to talk about how do you do machine translation at scale, right, for Indian languages. That's what my talk is going to focus on, which is our work on Samanantar, right? So let me just get into this. So what is the recipe for modern neural machine translation, right? What are the big tech companies doing today? How are you getting very accurate models for machine translation? So there are these 3 parts to it. One is data. So you have a large number of parallel sentences between English and Indic languages. I see a lot of our language experts here, and this is what you are contributing, right? So you're helping us create these large number of sentences where we have English sentences and their Hindi translations. When these are fed to a machine, the machine understands, oh, wherever I'm seeing home, I'm seeing ghar here. Or wherever I'm seeing I'm going, I'm seeing ja raha hoon or ja rahi hoon in the other side. So maybe these are translations of each other. I just learns this from a large number of such training examples. The operating point here being large, right? And that's what we did. We scaled a large number of such examples from the net, and that's what I'm going to talk about. Then we have models. So we built, again, large-scale models with innovations specific to Indic languages, and I'll talk about what those innovations were. And on the evaluation side, what is driving science today is the presence of robust evaluation benchmarks which have a diverse set of examples. Right? Again, for the language experts, you see that we ask you to translate sentences from multiple domains. Right? You get this multi-domain task because we want benchmarks which are diverse. Right? And it's not only enough to be good on children's stories, but we also want to be good on science and technology articles. Right? So that's where the diversity comes from. Right? Now, let's see what we do. So there are these 3 parts, right? Data, models, evaluation. So let's see what we did to solve the data problem. So we went to the web sources. So if you can imagine, right, in India, there's a lot of content on the web, right, which is accidentally parallel sometimes. So now if you look at news content, right, if there's a major news event, right, consider a very simple sentence, not even a major news event, right? The police grabbed the culprits. Now somewhere in some news article, this sentence is there in English. It should also be in Hindi in some newspaper. It should also be in Marathi in some. It's just such a common sentence, right? It has to be there. Now, if you just look at all the data on the web for Indian languages and try to devise mechanisms such that you can automatically find these pairs, then you could glean a lot of parallel data from web without putting in any manual effort, right? That's the basic idea that we have. And the rest of it is just a bit of jargon, so I'll just go over it. So yeah, on the web, you have what are known as comparable sources. Let me just go into that. So these are machine readable sources. So what we call is machine readable is anything that you typically read on the browser, right, which is readable in text format, as opposed to a scanned image, right? So a lot of parallel data is locked in government organizations, right? So, for example, our parliamentary proceedings often get translated to multiple languages due to various mandates and the constitution and so on, right? Now, when they get translated, often they are not put out as machine readable files, but they are scanned because someone then signs on them. So you create the document, you print it, someone signs on it, then you scan it back and upload it, right? Now, when it's scanned and uploaded as an image, you can no longer search or read that, right? So if you have a scanned document, all of you would relate. If you do a control F and try to find a word in that, you cannot find it, right? Because it's an image. So that's what I mean by non-machine readable articles. And these are typically coming from various government sources. And the machine readable articles are coming from news sources. This is what you read, news items that you read on the web. And if you search for a word in that, you can find that word, right? So that's roughly what machine readable and non-machine readable means, right? And what I'm trying to show here with these pink markers is that just by accident, if you just collect all the news articles in English and all the news articles in Hindi, then there are bound to be some pairs which match. And those are the pink pairs that I'm trying to highlight. But in the government documents, or documents which are not accidentally parallel, but have been created to be parallel, these are maybe advisories on COVID, which have been translated to multiple languages. These are, as I said, parliamentary proceedings, or these are maybe tourism guidelines, which have been translated into multiple languages. So there you can see that the intensity of the pink lines is more, because there is more parallel data there, because it has been manually created, right? It's by intention parallel. So this is what we try to extract from the web, and I'll tell you what the technology used for that was. The last, we have non-comparable corpus, which is I just take all sentences in English from the web. By all, I mean a large number, right? Of course, all is not defined here. Similarly, I take a large number of Hindi sentences. Here again, just by accident, someone in Hindi would have spoken about where was Mahatma Gandhi born. And similarly, someone in English would have written a sentence about where was Mahatma Gandhi born, right? These two sentences are lying in their independent worlds. But if we just collect all of them together, and if I have an efficient way, hey, here's an English sentence. Can you see in the English-Hindi collection, if I can find its parallel, then we might be able to get out these parallel sentences, right? So that's the basic philosophy. There's a lot of data on the web. I don't want to talk too much about technically what is there in this, right? I will talk about it, but the main idea is to impress the philosophy here that there's just too much text on the web which is bound to be parallel just because there is a large amount of data. Yeah, there might be some sentences in English which are there in multiple languages just lying on the web. We just need to find them and pair them up, right? That's the basic idea that we use. And how did we go about doing this? And how do we solve the data problem? So let me take an example of news, right? So you have this website called mikehill.com, which publishes sports news in the Indian context. And it also has a Hindi version, which is hindi.mikehill.com, right? These are not necessarily articles which have been translated. It's not that someone wrote a news article in English and then translated to all the languages. But say if there is an article about someone winning a gold medal in CWG or any of the primary competitions, right? Now, people would have reported that in English. People would have reported that in Hindi. And there's only so many ways in which you could say that someone has won a gold medal, right? So now if you just take all the articles which were published in Jan, in English and in Hindi, right? I've taken all the articles. I've extracted all these sentences from them. Now this is where it gets a bit technical. What I'm going to do is, I'm going to figure out a way of converting these sentences into points, okay? How I do that is not important. I just convert them into points. There are methods available for doing that. And I also convert all the Hindi points, Hindi data, Hindi sentences into points, right? Now just imagine all of these are points in some 2D plane. All of you can relate to this XY plane, right? We just have points. Now all I need to do is check if I have cases where a blue point is close to an orange point within a certain threshold. And if so, I'll mark this as a parallel translation pair and I'll just extract it, right? So what I'm doing here is a semantic match of sentences across languages. Right? So if I have an English sentence, I just try to extract a very abstract representation of that sentence. I extract a very abstract representation of the Hindi sentences, and if these two are very close to each other, then I just mark them as translations, right? And there is work in the past which allows us to take sentences and convert them into those points, and that's not something that I'll go into, right? And we did this across 24 such news sources from all the data in these 24 news sources. So My Khel is one. You could have Times of India. You could have many other newspapers, and all the data from 2010 onwards. Right? So we took 10 years worth of data, all news articles published in all the Indian languages, and using this particular figure that you see here, we were able to extract a lot of sentences. The other thing that we did is just not news articles, but all the content on the blog, on the web, right? It could be Wikipedia, it could be blogs, it could be newspapers again, or whatnot, right? And as I said, I was saying that we just, so we, in particular, right, we took some 100 million sentences in English, some 64 million sentences in Hindi, again did the same thing. Just took all these sentences and converted them into points. This process of taking sentences, which is English, into points, which is maths, is something that needs a bit of understanding, but again, I'll not go into that. What is important is that there are tools available for doing this. We just did that, we put them. Now, once you have this, all I need to do is find pairs of blue and orange points which are very close to each other. If they are close to each other, I'm going to call them a translation pair, right? And now here, what is known as brute force search, right? So imagine that I have a list of 100 million items, and I have another list of 64 million items. If I were to take every item in this 64 million and try to search it along all these 100 million articles, then this is going to be an exponentially difficult problem, right? I'll have 100 million cross 64 million searches happening, and I cannot do that. This is no way of doing this efficiently. Right? So what we used is what is known as the Facebook AI Semantic Similarity Index, which again organized these points in a nice way, such that if now I query one word, it does not have to look at all the 64 million sentences in the other language, but it can quickly do a search where it's only looking at parts of the data, and it's doing it in a very efficient manner so that within those parts, if a match exists, I will find it, right? So you're not compromising on accuracy, you're just scaling the search, right? And what goes behind, and that's what the green boxes are showing, is that I organize the data such that I don't need to compare with every element, but just compare with these green boxes. And there are fewer of those, maybe hundreds or thousands of those. So every point I just compare with these boxes. If it matches, then I find something within that box which might be an accurate translation, right? So that's the idea here. And using this, we were able to extract 33 million parallel sentences from the web, right? And there's a 3x improvement over what existed earlier. So the blue bars that you see here are the number of sentences, the number of parallel sentences that existed before our work. And the orange bars are the number of parallel sentences that we contributed, right? So across all the work that had happened, say, in 15 plus years, there were 12 million parallel sentences available across these 11 languages, Indian languages. And now we have added 33 million more sentences, for 3x improvement in the size of the, like a 4x improvement in the total data, but a 3x contribution from us. And this, I'll show later, made a huge difference in the performance, right? Now, what we did is once we had this, I spoke about on the model side, we made India-specific innovations, right? So what are those? We used a standard deep learning model, which is known as a transformer-based model. And the innovation that we did, and this is again has been tried in various contexts by other people also, is that we mapped all Indian languages to a common script, right? We just mapped all of them to the Devanagari script because H is there in all Indian languages, right? Ch is there in most Indian languages. Of course, you can argue that R in the South Indian languages, there are a bit more R and then what we have in Hindi. But we figured out ways of approximating that in some way and getting around the problem, right? And that approximation did not hurt. What it helped is, now if you have the Assamese and Bengali, right, which share a script which is Bengali, right, there was some transfer happening from Bengali to Assamese. What that means is that because I have large amounts of data in Bengali and smaller amounts of data in Assamese, and a lot of our languages, maybe Assamese, Bengali may not be the right examples, but a lot of our languages, say Marathi, Hindi, so they share what are known as these tatsam words, right, which come from Sanskrit, right? So now if I share the script, then these tatsam words can help in translating or sharing some knowledge across these languages, and that's what we observed. And we saw better performance for the low resource languages, right? So this is what our performances look like. So we have state-of-the-art performance. Again, don't go into the details, right? So state-of-the-art performance across all the languages on public benchmarks as compared to even commercial systems at that time, right? Again, all of these are point-in-time statements. As people keep moving the needle on science, these statements will change, right? Someone else will become better, and I'm sure we'll catch up again. But at that point, at the time of publication, this was the state-of-the-art or the most accurate open source model, right? So that's the summary of what we have done in translation. We have collected the largest parallel corpus for 11 Indian languages, and using that, we have trained state-of-the-art translation models, which, as I had mentioned in the morning, are now being used in downstream applications, such as translations for the Supreme Court.